The computer revolution has led to an information explosion. We have rapid access to more data and more knowledge than ever before, and our computer programs are bigger than ever before. Now we're faced with the problem of understanding and managing these huge programs and all this new information. Knowledge bases in computer programs are often difficult to understand just because they are so large. SemNet is a research project that explored new approaches to communicating large structures such as knowledge bases. Our goal was to develop a system that would make it easier for people to understand these structures. We borrowed methods and theories from computer science, cognitive psychology, and measurement theory to answer questions such as, how should large knowledge bases be presented to the user? How should the user explore, manipulate, and modify these knowledge bases? We knew that we needed a way to display a structure that would allow a user to look closely at one part of the structure, with the remainder of the structure shown in less detail but still visible in the background. Then we recognized that this is exactly the view we have when we look at an object in the real world. So in SemNet, structures are represented in a three-dimensional space and explored by navigating through this space. In this videotape, I'll show you how we represent a structure in 3 dimensions, how objects are assigned positions that reveal the organization of the structure, how information is compressed in very large structures, and how we navigate through a 3-dimensional space.
SemNet provides a rich environment for exploring and manipulating knowledge bases. Here we will demonstrate just a few of its capabilities while we focus on the research issues that we have explored. This is the SemNet environment with some of the tools we use to manipulate knowledge bases. We have just loaded a small part of a sample knowledge base. Knowledge elements are represented here by labeled rectangles, and relationships between these knowledge elements are represented by color-coded lines. The entire knowledge base is displayed in a virtual 3-dimensional space. I am demonstrating one of the several methods we have for manipulating the knowledge base and our viewpoint of the knowledge base in the 3-dimensional space. This particular method we call the helicopter model. It has independent controls for roll, pitch, yaw, and forward and backward movement in the space. I just pulled up a tool from the top of the window to control movement in another manner. This is called the absolute positioning tool. With a mouse, we can move the viewpoint around independently in XY or YZ plane. Here I am moving a particular node. I can grab a node and move it to any position, including pulling it way forward to make it easy to read. Now up to this point we have been looking at a rather small knowledge base. In general, we need to understand much, much larger knowledge bases. Now I'm going to read in the rest of this sample knowledge base. You can see that it is rapidly beginning to fill in the entire display. We are looking at a knowledge base of prologue rules organized into modules. As more and more knowledge comes into the knowledge base, the scene becomes more and more difficult to understand. So we need methods to manage the complexity of knowledge bases to enable us to understand them. We can move the viewpoint around in the knowledge base, and this allows us to understand a few of its components, but in general what you find when looking at a knowledge base like this is a feeling only for its true complexity. Now we're going to see that there are several techniques for controlling this complexity and revealing its underlying structure. First, we will grab a tool that controls the nodes. The first action we can do then is to turn off the annotation of the nodes. We can also reduce the size of the nodes, which further reduces the complexity of the scene. We can also reduce the thickness of the lines, but then this would make the scenes difficult to see on a videotape. We have also explored techniques to make the three-dimensional nature of the knowledge base easier to see. When the viewpoint is changing, we can see that the knowledge base is three-dimensional. So one thing we tried is a vertical oscillation of the eye point, a technique used in molecular modeling. We were not too pleased in how this vertical oscillation method worked out, so we tried another technique called the autopilot method. In the autopilot technique, we just turn on a random motion, and the whole display continuously moves around in very small random movements. Because the motion is small, objects do not move out of the view, but at the same time the motion contributes to a perceived three-dimensional view of the entire structure. Next, we will look at techniques to determine where objects should be positioned in space. When we initially read in the elements were positioned randomly in this space. And there may well be better positions for objects. For instance, objects that are connected together should be located close together. Here we are looking at a relaxation technique. That is, moving objects closer together that share similar connections. This is subject to a constraint that the objects will not be placed on top of other objects. We can also choose some objects that serve as anchors for the knowledge base. We fix the positions of these objects, so while the objects move around to be closer to their connected neighbors, these particular anchors will stay at fixed spots and the objects connected to them will be moved towards them. Those objects that are equally connected to more than one anchor will be moved between the anchors. It would make sense for someone to define these to be points that have particular significance to their knowledge base. For example, a manager might define the current project as an anchor, and the objects most closely related to this project then would be moved to surround it. Once the relaxation algorithm finishes, I will turn the annotation back on so we can explore the results of this relaxation method. As a consequence of the algorithm, the arc lengths are very short, and when we look at a particular object, we can find all the objects connected to it just by following the arc lengths. Next, I will demonstrate the most effective method for managing the complexity of a large knowledge base. But to really appreciate its power, let's move all the objects back to their original random positions. We can dramatically reduce the complexity by switching into cluster mode. Here the entire space is broken up into subvolumes, and each volume is represented by a single node. When we back up from the entire space, the cluster nodes form into higher level clusters. When we move in again, the clusters decompose to their subclusters until finally we get down to the level of individual knowledge elements and the arcs that connect them. In this view, we see a combination of clusters and individual knowledge elements. So we can still access the individual knowledge elements and can get rid of all the complexity of the other knowledge elements by keeping them inside the clusters. In the cluster mode, we often use a movement technique that allows us to follow the links connecting one knowledge element to another. When we select an object using this method, all the objects connected to it by links move close around it. If we select one of the connected objects, then we slide to where that object was originally, and the objects connected to it move in. We can use this method to follow the links through this entire semantic network. We still have the entire knowledge base behind the clustered objects, and the clusters have simply reduced the complexity. Here we see the same knowledge base without the clusters. Now I will demonstrate how SemNet can be used as a knowledge base debugger. Here we have a simple test knowledge base representing an English morphological analyzer. In this knowledge base, each node represents a list of rules. In the arcs represent paths that messages can be passed between these lists of rules. Each node in each arc has a set of states that are represented by color coding. During firing, the node passes messages from one to another, and these messages are represented dynamically by a small graphical object called a sprite that carries the message. You can see the sprite following the arcs between nodes. The color of the arc represents the success or failure of the message as processed by the current node. At times when the sprite is difficult to read, a special little menu shows the current value of the word being processed. We can take a close look at a particular section of the knowledge base and see how the sprite is represented and what the consequences are. Here the node plural noun is processing the message grandfather, and failing to find a match for grandfather, it sends a message to plural noun other, which returns the message failure. It didn't find a match for grandfather. Now grandfather will travel along other args to be processed by some other part of the network. When a linguist finds an error in the knowledge base using these methods, then the rules comprising the nodes can be inspected and an editing menu can be pulled up to manipulate these rules. For example, cutting one of the rules out of the list. Finally, we show the capabilities that SemNet provides over its own environment. We can adjust the colors of the background, the colors of the nodes, and spin around the entire knowledge base. So SemNet can not only be used to do interesting work, but provide an aesthetic experience for its users.
SemNet was intended to help users recognize and understand the structure or organization of a large knowledge base. To expand an old aphorism, SemNet attempts to reveal the structure of the forest, not details about trees. Because this research explored uncharted territory, our emphasis was on identifying and formally evaluating many alternatives instead of conducting formal evaluations of a few alternatives. A longer-term objective is to develop a generic approach to understanding knowledge bases by combining and optimizing the best solutions. But SemNet is not intended to solve all knowledge base problems by itself. It is intended to be used in conjunction with an application program that provides access to the contents of the knowledge base elements. Other potential applications of SemNet are communicating the structures of large projects, debugging object-oriented programs, browsing through hypermedia documents, and representing connectionist models.